think we are going to start. So I decided not to use slides so that we can discuss, because essentially I already gave a seminar in the first workshop, but maybe some of you were not there. Anyway, they asked me to, I think was something interesting for somebody, discussing with somebody of you, so maybe we can go on in some detail on this variational approach. So this is good. Student of mine, which is Nicholas. So the goal to, I think the goal will be to study the phi 4 in measure on torus, and essentially the idea would be to be able to define which formula is given by interaction and okay, let me new is the Gaussian measure Gaussian with variance, okay, with covariance given by the Laplacian plus the master. Put it at one. We don't really care. So this is the Gaussian free field on the torus with some mass, and you want to, okay, this is something we are going to say all the time, so I'm not spending much time. Okay, you would like to define this object, and the interaction potential for many reasons has to be taken local, and so we take something like lambda phi 4 minus, and then we will need to add some context. And then let's add something else. Of course, all this is formal, okay, so I will just change in 2 seconds the formula, because we will need, okay, to make sense. Up to now, I think we looked at this renormalization group point of view from the point of view of a single scale. So you just look scale by scale, and then you get estimates. So you never see irregular objects, okay? But here we are going to look at this object more from the point of view of PDE theory, okay? So even if there will be no PDE, okay? But the idea would be that really you would like to deal with distributions, and so this is measure on the space. Okay, you can take S prime of the torus, but essentially mu is on something which looks like C. Okay, you can choose the space. This is not canonical, okay, but maybe we will look at things like C to the minus 1/2 epsilon on the top. Okay, so this means that they are distributed. So I will maybe, if you ask, you should ask question at some point, okay? Because maybe something is already clear to some of you, but of course maybe not. Okay, so this looks like, I don't want maybe at this point to give all the definitions. So this looks like you should think the sample part as something like distribution of regularity minus 1/2 in some order space. Okay, so you measure with some L infinity now. So, which means, so in particular, that this integral does not make sense. Okay? So you have to regularize, so, and this we look, so we have to regularize all these things, so we just look not really at the interaction in the field, but we regularize the field with the parameter t. So Pt is just rho t equals with t, and rho t is some regularization. Okay, so some smooth function, which is normalized. Now I have to take And so you have, and this is smooth. Let's move for now, this is smooth, this makes sense, but of course then when we try to send t to infinity, we will have problem, and we already know that we will have to renormalize. So actually I need to consider a sequence of potentials. Okay, so this is the bare potential, is the potential at the scale, the smaller scale, so from the point of view of renormalization. And so you need to have this constant dependent t. B is not really needed because anyway there is the renormalization, okay? But for me, I will need it later because I want to control independently numerator and denominator. Okay, just to decap or...
So t goes to 0 or goes to infinity?
Yeah, no. Yeah, you're right. Okay, now I'm confused because I was reading paper of Hendrik and he has t going to 0, but I want t to go to infinity. So let me... I have to normalize it. So I want t to go to infinity. So let me... I think it's okay. Yeah, so, and we will have t to go to infinity. Yeah, so. Okay, so this is the setting, and the goal is to, okay, for this talk, we're going to prove uniform bounds, okay, on, for example, ZT. So, prove uniform bounds on something like, okay, so you take some test function, you compute on phi, and then you add your potentials, so lambda potential, and then, okay, so this is the goal. We want to prove uniform bounds on this quantity, and this is called E minus WT. And okay, so we are going to look at this so as I told you, I want to look at this problem as a PDE problem. Okay, try to reuse the technology we developed for handling the stochastic using PDE tools. Like for stochastic integration. Like Hendrik said, okay, you have to, you would like to see some expansion, and then you control every term, and then you try to bound everything. Okay, so in this sense, in the sense, but there is a relation with the renormalization group point of view, of course, because essentially the object you try to control is the same. Okay, here I'm not looking at the effective potential, I'm looking more at like the generating functional for the, so it's some kind of Lagrange transform, but this is, I think, can be just, I mean, you can also look at effective potential, just convenience is not much more complicated. Okay.
Excuse me, SQE is a stochastic quantization of
equation.
E.
Okay, if E perturbs you, then you remove it. Okay. So it means that the PDE, okay, the PDE that has this as invariant. Okay, so something like this. But I will not write down, I will not use it actually, okay. Okay, so this is I will not use anything in particular. So, okay, let's go. So the main tool now, to do this job, I need somehow I need this decomposition over scales, okay? And instead of doing this like in the renormalization group in a discrete fashion, we're going to do a continuous multi-scale decomposition of phi of t. Okay, so what you want to of phi. Okay, so you would like to see this phi as the result of summing fluctuation in different scales. Okay, so in order to do so when you need to add the fluctuation in different scale in an independent way, there is some Brownian motion going on, okay, because you have a sum of independent things. And so one way to set up things is to imagine that one has, so let me just check my notations, because otherwise. Yeah, so you imagine that you have now you have a process x3, which is a cylindrical Brownian motion. Cylindrical Brownian motion on L2 meaning that at every time is distributed like this space white noise on the top. Okay, so this means that xtx, x, it's a Brownian motion in T, and okay, formally at least so this is like the source of independence random variable. Okay, you want independent in time, so it's just the integral of the space-time, not. But this time, so just I call it time, but it's not time. Okay, we play the role of a scale. For the moment, it's just an additional parameter I introduce in the problem. Okay, I call it t. And then you define. Okay, now you will not write down all the formulas. Okay, but essentially you can define now a new process. I need to color this. Okay, because what I want to produce is something with this covariance, okay? So you define a new guy, and this new guy is some coloring of, that's okay, so you need -1 and then now you want to add fluctuation in a progressive way, okay? So now you use these increments. So these are like independent increments, and you need a function which says that at a given moment you just need the fluctuation around a given scale. Okay. So you want a function, I call it sigma s, and then here I put some d, and this is Fourier multiplier. Okay, so the meaning of this thing is that when it acts on a function f in Fourier variable, this is just multiplication with this function here. Okay? And you have to imagine that sigma s of k looks like the following. Okay? Around s, it's just a bump function around s. Okay? It has to be arranged in some way at the end, but I will tell you later. Why we do, okay. Okay, so this means that, okay, so what you're doing, you're taking this space white noise, then you are just looking at frequencies around the frequency S, and then you color it, okay, and then at the end of the, and then you integrate in time, okay, you just sum of these independent contributions. So at the end of the day, what does it look like? It looks like, let's try to compute how does it look like. So this would be a distribution, so I need to test the test function and another one. It's really this multi-scale decomposition we saw in all this, just in a continuous way. Okay, so instead of having sums, you have an int. And how does it look like? So of course, of these two time, only the smallest wins because you have the integral. So it looks like f, and then you will have these two contributions. So everything is diagonal. So I'm just computing more or less formally. Actually. And then you will have the integral of sigma s d to the square ds, and then you have g. Okay. Something like this. Meaning, okay, if you want, meaning that if you look at this in Fourier space, then it looks like this. And then the integral. And now you are, so at the end of the day, you would like that this object has the same law of this guy. Okay, so what you need to arrange is that this object, I can choose sigma so that this is a rho t scale. Okay, so this I can arrange sigma. So it means that this will be like something like the rho t. Okay, so essentially this would be, so in particular, yt has the same law of phi. Okay, if you do this choice, okay, that's the point. So this is a coupling, so if you can look, y of t is a coupling of all these random variables. Okay, they are set up in the same probability space. Is it different from that? Okay, also this is a coupling, but this is a different coupling of all these random variables. Okay, you see on this on the probability space of phi, of course you can look at this as a process, but this is a different process than that one. Okay, only in law they coincide. Okay? Because here I sum in independent contribution on different scales. Okay, here all the randomness is coming from a single object. Okay, you're just filtering the values. Of course, they are almost independent, but they are not exactly the same. Okay, you can compute. You can compute the correlation between 2 times here and there, and you see that they are different. Okay, so this is my coupling.
So T is the minimum of the T and S, and S, which is not the integration variable.
Yeah, sorry. Yeah, I understand. Let's call it T prime. Okay, so this is T and T prime, and then you have S. Sorry. And here also we have T. Thanks. Okay, so this is our coupling. Okay, and now you can write the same formula. Okay, so our function looks like. And now I use expectation to denote the expectation on the canonical space. This is linear space. Okay, on the canonical space for the Brownian motion. I need this setup. So everything is written with respect to this Brownian motion. And you have just to realize that for finite t, everything here is finite. Okay, every sum is finite, everything is well defined, actually quite elementary. Okay, well, the Brownian motion are just finite dimensional. You don't really need this in Brownian motion as soon as t is fine. Okay, and then you have the same expression. And now I can call it, now I want to use this. Okay, so I call it y. So here I didn't put any, on the test function you don't need to put any, because you can assume that it's well defined. I mean, f is just a function. F you can imagine is a function of f1 of t, right? And here you can check that you can take the limit to infinity, okay, when infinity exists. Because essentially when you take the integral to infinity, this becomes 1. Okay? And this is actually the phi infinity is the graph. Okay, so here you have that, and here you have v of t, and then y of t. So at this point I have this kind of dynamics I would like to work. Okay, so let's put this on the side for a moment.
So
And
when you write f of y, that's a linear pairing, is that right? Or
you don't know, it's a generic function. Can be, but if you want to think a linear pairing, can. But okay, I can defend this for any f.
okay,
It's a generic function.
but it couldn't be phi to the 6, right?
Okay, yes, bounded. Yeah, I think, no, 5 to the 6, no, unless it has the right sign, but it can be pretty generic. Okay, let's say bounded. That, yeah, I need some property, but I don't need boundedness. As soon as some other quantity is under control, it's okay. But okay, let's say it's bounded. Okay, or linear group. Or linear group. So this is a Yes, of course you cannot screw up. But the important thing is that it really depends in a nice way on the and for the moment you actually, I mean the problem is already interesting, even f is not there, okay, so you can ignore it. I will ignore it later on actually to do all the rest. Okay, so and then now the second ingredient, so this is another ingredient, this is the Bouvet duplicate. Okay, and this has nothing to do with this problem. It's a generic formula which was proven by these two people, and looks like this. Okay, so you have a Brownian motion. Okay, X is a Brownian motion on its canonical space. And f is a functional of the Brownian. Let me not, I mean, I will apply to our situation, but so looks like this, minus logarithm of the expectation of e of f of x. So this is a generic functional of the Brownian motion, okay? Could depend on the whole trajectory. And then you want to evaluate this expectation, and you take the log because you like it. There is also minus here to. Okay, here it depends on what you want. And then now, this formula tells you that expectation of this kind, which are pretty much every expectation essentially, looks like a variational problem. Okay, so this is the infimum of controls. Of what? Of f of x plus, so let me, I will plus 1 half the normal view. Okay, so let's think about it in finite dimension. Okay, so it's let's see, it's a Brownian motion on RD, but the formula holds in Hilbert space, and we will use it. And f is just a functional from this is the canonical space, say, from trajectory 0 to infinity. Brownian motion, maybe I don't have the right idea. The function is here to up. And so what is, so this is the form. What is HA? HA is the space of adapted. Wow, okay, progressively met. So they adapted to the filtration of the Brownian motion. Okay, here we are in a canonical linear setting. Okay, you have a canonical space of the Brownian motion. Canonical space. Okay, canonical. Or Brownian. Here you don't care, but essentially here you start to care about who is measurable with respect to who. And the only information we want to care about is the Brownian motion information. Okay, so you have a function of the Brownian motion, and you can write in this way. So it's you need to take the infimum, so it's a optimization problem of the functional with a shifted Brownian motion, and you pay a price to shift the Brownian motion. Okay, so the price is the L2 norm of this process. Okay, so this is just the integral. The integral from 0 to infinity of u squared. Yes. Okay. And what is I of u? So this is just the embedding. So this is like the norm on the Cameron-Martin space. Okay, so you have to go back to the trajectory space. So in this case, you take L2 as Cameron-Martin space, and then to go back you have to integrate. Okay, so this is like a process which at time t has the value qs. Okay, so this is continuous function of, and you have an estimate for the order not. Okay, so you have like ITU minus the normal viewpoint, this is embedding, how does it work? Okay, so this is, but the idea is really that U is in the Cameron-Martin space, okay, and then I of U is how you go back to the trajectory space. Or you can decide the Cameron-Martin space is H1, and then you don't have to, you don't need this map here to go back, okay? But then you need the H1. Okay, so this formula is it's general, okay? It does not depend on our code, okay? But I always find it very nice and try to apply to every problem I can. At some point, you find a problem where it fits.
So this is just a change of variables while it gets
No, it's a theory. It's a theory. The initial proof was quite complicated, actually.
Let's say if we're happy to do this on R instead of Brownian motion for a one-dimensional Gaussian. Right?
It does not work. No, we discussed it. Okay, let's discuss this, because I can spend all the time discussing this formula. Okay? Because no, the proof is complicated. There is an easy proof for a different formula. Okay, because here the complicated things is the measurability. Okay, actually. There is another, so the easy formula which requires this easy version.
No, but I'm asking something much easier. If you replace Brownian motion by a finite dimensional Gaussian vector,
Yeah.
then we presumably have an analogous formula.
No, I don't think so. I don't think so. So if you replace, so this is like, so inside there is a Gaussian theorem, no? So Gaussian theorem tells you that, okay, let me give you the easy version. So, because, I don't know, I mean, maybe, but even the easy version does not have a finite dimensional. So let's discuss the easy version. Okay, the easy version is as follows. Okay, you can define. I can discuss this formula all the time. The easy version. Okay, let me be a bit fast. Okay, because maybe I don't want to spend all my time on this. But the easy version would be, I define this measure. Okay, and then you take f bounded, so this is absolutely continuous, and then there is Gaussian theorem tells you Gaussian plus the Brownian representation, martingale, Brownian martingale representation.
You normalize that measure, no?
No. Yeah, maybe yes. Wait a minute. Yeah, I have to normalize that. Yeah, normalization. So Gaussian theorem plus no, sorry, I don't need Gaussian yeah, I mean standard computation with martingale plus the Brownian martingale representation property tells you that this density can always be written as a Gaussian exponent. Okay, so there exists a drift, let's call it V, such that this is something like this. Okay, and maybe integral up to infinity if you decide that you go to infinity or whatever. That's I mean that's using this property. That means that every martingale on the. That's why I need the Brownian setting. Okay, because I need to know that. From this you can get a positive martingale, and then you know positive martingale have this stochastic exponential with a martingale, and then I want to identify the martingale part, and then I use the Brownian representation theorem to say that the martingale part has to be a stochastic integral. Okay, and so you have a representation like this. Once you have, so there is the drift, there is not even an optimization problem here. Okay, there exists, it's implicit and it's complicated, and you don't know how does it look like. There are some formulae in the Malyavan calculus, but there exists a drift which reproduces exactly this density. Okay, and this would be science. I mean, infinite dimension would look like a shift somehow. No? You do a shift. Maybe it can be proven with from this can be proven, but there are no so easy proof as far as I understand. Yeah, I mean, it is not obvious at least. Okay, there would be maybe it's a proof with the transport theory. You can prove that there is a transport map which send the Brownian, the Gaussian to this measure, but that's not so obvious. Maybe you.
So now you just
Actually, many things. This formula were used to prove functional inequality. Was used by Borel, for example. This kind of relationship were used by Borel to prove some functional inequality for the finite dimensional Gaussian. There are no. So that's why I don't think there are shortcuts, because you cannot. Even in finite dimension, you want to go to Brownian motion to prove some properties. So you want to embed your Gaussian as the final value of the Brownian motion, because then on the Brownian field, you see here the idea is that since you separate time in very many slices, cannot happen, not so many things can happen on a single slice, okay, only some very small translation. And so you can really develop this in that way. Yeah, that's my intuition. Okay, but okay, these were smart people, so if there is a finite dimensional proof, they would have used the finite dimensional version.
Well, maybe it just looks complicated, but I would like.
I mean, it does not even look complicated. For me, I mean, as far as my intuition goes, is that it's really the fact that there is Brownian motion, that the small interval nothing can happen helps. Okay, you cannot even replace with the how you say for random walks does not work. Okay, you don't have this theorem for random walks. Complicated. You don't have this problem. Yeah, I mean you have, but I mean it does not look like so simple. Maybe. Yeah. Anyway, okay, so this is the simplification of this plan. And the easy version goes like this. Okay, if you have this, then essentially now I don't remember the proof, but essentially you can do now you can do the Gilsanov theorem and obtain something like this. Okay, but it's not quite the same formula because so if you use Gilsanov theorem, so you have under Q, okay, the canonical process minus or plus. Okay, now when I have to think twice. So if you have, let's say this is no, I think it's minus. This is a Brownian motion. Okay. So you have a similar formula somehow. So the similar formula looks like this is a cube Brownian motion. So the similar formula would be that x can be replaced by a Brownian motion plus the drift. And then the entropy, and then you have another formula that is the entropy of Q with respect to P is 1/2 the expectation of this V squared. Okay.
Why do you need the entropy?
You can compute the
So
entropy.
then you just inserting
Because so you see that this term is really the entropy somehow of the measure of the different measure.
But if you just wanted to prove that formula, you don't need to ever write down that entropy.
I mean, you need something like this. I mean, the proof of the formula,
You insert this into your variational principle.
Okay, depends how you look at the formula, but yeah.
So presumably in a finite dimensional case, it would just not be sort of something that looks formally linear in x, the exponent, right? And then you can't really translate it away.
Maybe it should be like there exists a transport map which does the job, okay? But you don't know much about this.
Yeah.
Here he also, I mean, here you have ways to compute V if you can handle the Machiavellian derivatives, but okay, we don't care because our point is that I don't want to look at V because V is complicated. The drift, okay, there exists a drift. So what is the difference? So you have to see that essentially the I don't write down the easy formula, but the easy formula will look like, in the paper there is, so you can look into the paper, will look like this object there, f of, instead of being evaluated at x plus I of u, will be evaluated at b plus I of u. Okay, in law is not the same in law, okay? Remember, here v is adapted to x. Okay, v is something which is adapted to x.
Yeah, there's expectations on the right hand side of your big formula, right?
Yeah. Okay, so the easy formula would have here expectation. So the easy formula would look like,
Mine just went.
yeah, expectation under Q of f of v plus I of v. So actually you have v. Okay, so yeah, I think it's like this. But v depends on x. Okay, x is all this. Okay, plus 1/2 like v. So let me write. I here, of course, it's implicit because it's u depend on x because it's the canonical variable. Okay, but I can neglect. But here I want to emphasize. Of course, here too, b is a function of x. Okay, because here you are on the canonical space and you construct on that space a Brownian motion. So in law somehow they look the same. It's a Brownian motion plus some drift. Okay. But then when at the beginning I didn't want to use that formula. I wanted to use that one, and then at some point you get into your fit that the measure depend on your problem. And so technically it's harder to work because as soon as you start to change things, these measures are going to change, even if in law is the same. And there is no easy relation between B and V because V depends on X and B depends on X. So, but one does not depend on the other.
Why do you need that actually? I mean, for the upper bound and the normalization constant, you can work with that formula, no?
Yeah, I think the first version of the paper has been written with that formula. So maybe because I wanted to skip all this thing, wanted to make the paper self-contained. But then at some point when you start, when you want to take the limit, it's easier to work with a fixed space. That's why they look. I mean, the reason of this formula, the initial paper is quite long. It's complicated. It needs some kind of measurability proofs. Now there are easier proofs, but it's not obvious. And here there is a minimum. Okay, this formula is exact. There is a v which satisfies that formula. There is an if. Okay, so you pay the price to change this. But the advantage is that now that u is a function of x and x there is the real x. Okay, there is no. So the probability space is fixed. Is the space on the Brownian motion, and you are doing. You are shifting. Okay, here everything moves, and when you try to prove like convergence, then it's trickier. But for bounds is as good. But yeah, I mean it's. I think at some point. For the one of the bound, okay, let's go on. Okay, but just to say, yeah, you could try, but you have both options. Okay, now you know that there exists both options. Okay, so that's our formula, and we want just to use in our context. Okay, so in this, so now we have a formula for that. How does it look like? It looks like the W. So. Okay, you have an easy theorem. It's not really even a theorem. It looks like, but you have a representation. Okay, minus logarithm looks like the inf. Now I will have off on u. Okay, now there will be minus f. Okay, let me ignore f because it's not playing a large role. Okay, let me put 0. I want to care about v. Now you have v of t computed where. Now you have to think that this is not a functional of the Brownian motion. Okay, it's a functional of y, which is a functional of the Brownian motion. Okay, so here you will have, and y is a linear functional of the Brownian motion. Okay, so here you will have again y of t, because you have x, and then you have I of u. So there will be a contribution which looks like z of t, and I will write down what is z of t, and then you have the cost function. And now this is L2 of time and space. Okay, so because now you have this infinite dimensional Brownian motion. And what is ZT? So y of t we brought it. Okay, ZT is similar, is just 1 minus Laplace minus 1/2. Integral between 0, so up to 2, let's say. Sigma SD, and then you have US dx. Okay, just the drift you need to have. So I will try to use this notation. So Z depends on U. Okay, it's a function of U. It's just a linear transformation of U. Adapted.
So here you have an expectation again, no?
Yeah. Okay, this is how it looks like in our setting. Okay. So let me comment. So the idea is that this U, if you could find, okay, now in the formula we lose the minimum, okay, but the idea is that U represent the gradient of the effective potential. So you have to think about U as the gradient of the effective, for the people who know renormalization group, okay, so gradient of the effective potential. Okay. So this is from the point of view of renormalization group. Okay, is what appears quadratically in the formula for the flow equation. Okay, so it's the gradient of the effective potential. That's essentially the square. Okay. For PD people, if you want to have PD people, this representation tells you that, okay, the idea would be, of course, morally, okay, that phi t looks like yt plus zt. Okay, so you have these 2 points of view. Okay, you have a more potential theoretic point of view where you describe the potential, and then the u is just the gradient of the optimal. So the optimal u will give you just the gradient of the effective potential. And more trajectory-like point of view where you look at the sample path, and the idea is that the sample path of the interacting field looks like the free field plus some perturbation, which is solution to some variational problem. Okay? And this decomposition is like the decomposition you do really in the PD approach, okay, where you start with the solution of the linear equation and then you perturb around the solution of the linear equation. Okay, so this is what we are going to do here. So perturbation around the linear equation. Okay, so from the PD code. And that's why I say this is PD approach. So let's see how does it work into dimension. I wanted to do the 3D, but I think we have to see at least an easy computation. So let's see how does it work into 3D. So now the goal becomes, I want upper and lower bound on that quantity. So upper, lower bound on d of phi t plus t plus 1/2 u now I really look at this pathwise approach. Okay, I don't care anymore essentially about the expectation until the very end. Okay, I just look at this functional. This is a functional of U. It's a random because the randomness is here. U is a process. Okay, so we take omega and spit out a function, but essentially I look at this thing, and I want upper and lower bound uniform on U in such a way that then when I take expectation, I have a finite quantity. Okay? But the point is that I don't want to look into U because U is too complicated. I don't know how to express it. Okay? And so you look at this as a really like optimization problem, calculus of variation problem. This is the good guy. This is the guy. You need an inf. Okay, so upper lower bound are not the same. Okay. So for the upper bound, you choose a good function, okay, because you want an inf. And for the lower bound, you have to bound all the functions, okay? Upper exists a u, and lower for all u. Okay, so you have to, this is the game you have to play. Okay, so for the upper bound is easy. In two dimension, for example, I could take u equal. So let's look how does it look like this in two dimension. Okay, so I take b equal to, but okay, it does not play much role, and I can arrange a c such that. So now you can choose. Okay, you do a computation. This is a polynomial, so just the sum you expand, and then you have the renormalization, and you realize that you can arrange things such that it's functional. Let's move it to f of t. So f of t looks like the integral, and now you have the weak products. Okay, so okay, let me use the no, yeah, no, I'm not. So I denote in this way the weak products. Okay, so there will be lambda 1 cube t. Oh, no, there are all these and then there is one useful. Okay, there are integrals everywhere. Here, here, here. And and this denotes the weak products. Okay. So the thing is that you can arrange so that you have A, and maybe you have to treat maybe, no, I think A, yeah, maybe it should be T such that you can have this form. Okay. So these are Gaussian, okay? So the weak products is well defined.
Why do you need BT?
Uh,
I think for that one, you have to subtract a constant to have a weak
Ah, that's the
product.
constant.
Okay. But
It's not the quadratic term in.
No.
It's not the one that you need in 3 dimensions.
No, 3 dimension is more. In 3 dimension, you will have to do this, so we will restart from this, but we will have to do more processes.
So in any case, basically.
The first so there is a part. The first renormalization is always having weak products around in this formula.
Yes.
Then, but okay, now let's discuss it. Okay, this term I don't care. I could even not renormalize it.
It
I
has
don't care at all
expectations,
because no, I don't care even because it's not depending on you. Yeah, of course it has expectation 0, but even if it has finite expectation, I can subtract. The point is that it does not depend on you, so there is no optimization to do. I cannot do anything, either it's finite or not. And in this case, it has expectation 0 if you choose the renormalization constant. Now, these are the good guys, okay? These are good. These are good because they are positive, okay? So for the lower bound, I can throw them away. For the upper bound, I have to choose u such that they are fine. This depends on you, okay? But let me write in this way because it's not useful. If you, yeah, I mean, this is really the action, okay? You have to think of u as being like 1 minus Laplacian 1/2 of z dot. Okay, no, actually, is that modulo 1 sigma is that. Okay, so it's not really that. So now this good terms is really the good terms looks like gradient z. So it's not like that, okay, because there is this time derivative around, but you can think about it like this, okay? Plus lambda z L4. Okay. It's telling you something about. I mean, this is very. Okay, it's just intuition, okay? But the point, because there is this time derivative, but this time derivative means along the flow. So the idea would be is really that you have to consider this as a representation of the energy of Z. So, anyway, it's positive. That's good for us, okay? Because for the most difficult somehow is the lower bound. We have to bound every U. Okay, so something positive is nice. So now the game to play is the following, is that you hope that the other terms cannot be big unless this term is big, okay? Because you want to prevent, so now let's think about, upper bound in two dimension, it's easy, okay? So upper bound I don't even discuss because you can choose U equals 0 and then everything disappears. And that's finite. And the lower bound, okay, so upper bound, U equal to U equal to. Okay. But in Jensen,
So what exactly do you want to prove? So usually
I want to bounce upper lower bound for me.
So but suppose you wanted, say, the first or the first. I mean, this has an asymptotic expansion presumably in F, right? Can you the generating functional?
Yeah. Yeah. I don't know, maybe I can prove, for the moment we concentrate, because the idea is that this does not require lambda to be anything. If it's big, it's even better, because that's gets bigger. I will have estimates, or maybe I will not write down, but on the paper there are estimates which depend on lambda. We try to track down lambda. We can prove that, the correct, I think the free energy is of order lambda to the cube.
Right, but so is there any, if you wanted, say, the second term, I guess where you'd see the free field, I mean, I guess the first term in orders of lambda would be
Z would be of order lambda, for example. There would be a lambda in front of Z in 3 dimensions. In 2 dimensions, you don't see very much because.
How systematic can you make sort of good
Yeah,
answers
I
for
don't
you?
know. So
that was my
Is
question.
it easy? Or?
Yeah, I don't know. I didn't thought about having systematic. Maybe it's possible, but the point is that now the technology I'm using is like so here. I don't know. Maybe it's possible, but I didn't thought much about it. Because I look more as a non-perturbative thing, so I don't.
Yeah, but in 3 dimensions, you probably presumably construct some pretty complicated sort of answers for you. And this is a.
So in 3, I will tell you. Now in 3 dimensions, the point is that the field. So it will be yt plus, and then there will be a cubic guy, which I don't remember how we called it. We gave a complicated. Yeah, because at some point we just change it. Okay, let me write in this way. So some cubic guy, which has lambda in front, and then some guy which looks like quadratic in the field. There are complicated expressions. So let me say more.
What are you writing down here? What is
The ansatz for the jet.
So this is Z. Z looks like this. Okay.
Yes.
And something like Z here, and then something else. So I think it's systematic in this sense, but it's more about what we have in PD for the PD. We don't have much more. I mean, if you make me a precise question, maybe what is the?
No, I think it seems like you can. So at least on the level of the y's, it seems to be pretty.
I have bound, for example, for the free energy, I know that it's over the lambda to the cube, what it has to be in 3 dimensions when lambda gets small. So.
You mean?
For the WT. when you can do
If you
subtraction.
have the big constant already
Yeah.
in the, okay. But I guess you're constructing a bunch of constants on the way that have the lower order dependence. So the free
Yeah,
energy is
so-
all the lambda plus all the lambda
So
squared.
let me show how it works, no? Because, okay, even in 2 dimensions, so let's discuss. So now the point is that you have to prove that these guys can be bounded by that, okay? So this somehow control the powers, okay? Because this is quadratic, so we will have problem to control that term, okay? So this can control that term, but now the point is that these guys, so these are the stochastic objects, this is just free field composed with itself, okay? So they are distributions and they diverge so you cannot bound easily these quantities, okay? So essentially, for example, let's look at this one, which will have a limit. So this guy will not even have a limit. No, sorry, we are in 2 dimensions, so that's fine. Everybody has a limit, so I was thinking with the 3 dimensions. So this will converge to something, which let's call it my infinity cube, in c to the minus kappa. Okay, so kappa is just a small number. Positive small number. We are in 2 dimensions still, okay? Already thinking. So the idea is that all these guys are very, as far as integrability is concerned, are nice because they are essentially in an infinity, but they are distributions. Okay, so you need to use sum of regularity of z, and you have an estimate for z which looks like this. That zt can be bounded in H1. Okay, by ut. Okay, so this bound is ut. Okay, you have this bound in H1 because essentially is yeah, there is no square here. Okay, so you have a bound like this. Supremum, actually here you can put the supremum over it. This is uniformly bound by the du. Okay, so the idea now is that this provides you regularity for z and this provides integrability, and then you have to estimate this thing in mixed space. So for example, let's give an example. This guy, yeah, I mean, yeah, it's a then you have to be you have to know how to. Yeah.
So is that the only a priori bound you can write for Z?
Yeah.
That's the best you can do.
That's the only. I mean, as far as as far as regularity is concerned, yes, because that's the only information you have. Then you can interpolate these two, of course, but then the extrema of the regularity is this, and you have only in the 2 scales somehow, and that that's the, it's not like that's different from the PDE, because in the PDE maybe you have a regularity in different spaces, but here you have only L2 regularity.
Yeah, so I was wondering because this is a fractional elliptic PDE, right? If you forget the time.
Yeah.
And then I was wondering whether you could get
No, but
something
this is, I mean, it's natural also from this point of view. I don't see very much how to link with the regularity theory for the PDE, but from the point of view of this functional, you don't expect to be able to control higher. Because for the PDE, you can use Shaver theory to improve, but here I don't know how to do it. Maybe if you use more specific property, this is generic, okay? Of course, you are paying the price that you want to control every U. But then the optimal U maybe has a specific structure which you can then use to have better.
In 2D, you don't need to control every U, right? You can really just work with one. Well, no, because if you just want the...
I mean, you know that there is one, but you don't know how that looks like.
I don't
Even
really
in
bound it
2D.
independently.
But even in 2D, I don't know even in 1 dimension how this procedure looks like for me. So it's true that, let me say another thing, that these functionals we are looking at are special, okay? They depend only the finite time. So there is a Markovian structure inside, while the general formula does not care. But and so the Markovian, somehow, yeah, using the Markovian structure, you know that the optimal control is Markovian, let's say, from general. Yeah, you can believe that the optimal control is Markovian. So you should think that there is some functional, let's call it g of t of y of t, which delivers the optimal bound, I think. This is from general controller, but I don't know. This would be the derivative of, really the derivative of the effective potential at scale t computed on the solution. Yeah, sorry, because under this there is always this idea that if you look at the finite dimensional problem, there is the link between Hamilton-Jacobi equation and optimal control, stochastic optimal control. And so there is somehow dictionary to from how it looks like the Hamilton-Jacobi equation and how it looks like. And if you have a solution of the Hamilton-Jacobi equation, then I know what is the optimal drift I have to put, because it's the point of having the Hamilton-Jacobi equation tells you what is the optimal. And the optimal is given by the gradient of the solution of the Hamilton-Jacobi. Okay, so, and in a Markovian way. Okay, so you could look, if you want to solve the, I mean, if you have a solution of the RG equation, then you have a solution somehow of the Hamilton-Jacobi equation, and then you can plug inside this to get the estimate. But the point of this is the opposite. That is, I don't want to solve the Hamilton-Jacobi equation. I want to get information on the Hamilton-Jacobi equation from the variational problem. And so the only way to play this game is that I don't want to start to look into U, because otherwise I would need to have this more refined information. Yeah, I think that's. Anyway, so I was estimating this, no, and then how this looks like, just if you want to see it. Then you have to do functional analysis. No? You have to look and how you estimate this thing with the L4 and H1 norm at Endor, and then like this term can be estimated like yeah, I mean something like lambda, and then you take the norm of this guy in like some fractional. Okay. Let me also tell you some. So these are some fractional subpolar space, and then you have norm of z in W12. So this is H1, and then you have L4. Okay. And now you use Young in the right. Young's exercise for you. Use Young inequality in the right way, so that this guy got a lambda in front, so that's the only complicated part. Okay? You have to have the right power of lambda in front of this guy, because you need to absorb with that guy, okay, which has a lambda in front, and that's fine. Okay, that is fine. So essentially now. Yeah, you could put the older norm here, okay, but it's not very wise. You could do it, it will work, but then when you start, if you want to prove that, for example, this object is extensive in the volume, you will have a problem, okay? Because the older norm is not extensive in the volume, okay? You lose a logarithm when the volume grows. But the Bezos norm are fine.
But
Okay.
there's nothing special about 5. It could be.
No. I mean, it can be larger, but at least 5. You need, okay, because I think. And okay, then you do this estimate, and if I believe this number, there will be lambda cube. Just to show you how they look like. Okay, it's not very important. To the power 4, because all the estimate looks the same. And then you need to have a small delta, and then you have like ZH1 square and lambda Z L4. Okay, and now you are happy because then with a small lambda you can absorb in this term. Okay, would not go far. And yeah, you see, you generate these terms like this. So now when I take expectation, I will be able to bound with the expectation of this, which I can show it's finite, and the expectation of, and I get some powers of lambda. So I know that when lambda gets small, it's getting small, but then if you need more information, I think you have to do more complicated stuff. Yeah, and okay, so this can be absorbed. And when you finish to absorb all the term, you throw away the good terms because they are not useful anymore. Okay, so in 2 dimension, essentially this prove upper and lower bound. Okay, so this prove lower bounds. Okay, now I don't know because it's already noon. Do we continue? Usually, yeah, half an hour. Anyway, if you want to go, that's the main message. Now we start to look at the serious program. Now, if you want to work in 3 dimensions, it's not so easy, okay? And the part of the problem is linked to the fact that the limiting measure, maybe, is not absolutely continuous with respect to the Gaussian. I don't know if you tried to prove, Hendrik?
No, I claimed that it was part of your paper.
Ah, okay. Yeah, I don't know. Now we are fighting with gamma convergence, which is not working yet. This is the proof. Anyway. Okay, so let's look at the equation. But the equal 3 is interesting because what will proof is not finished, okay? But the point is that I think I'm reasonably convinced that it will work, and you will have a formula for the Laplace transform of the measure, even if the measure is not absolutely continuous with respect to the Gaussian, which I find interesting. But gamma convergence is tricky. Still not really working very well. Okay, so d equals 3. Now, what is the problem in d equals 3? The problem in d equals 3 is that this guy does not converge. Okay, so when all this game is to estimate uniformity. Okay, so you see here you can control these powers in this space uniformly in T, and that's the game you play. So this cannot be controlled uniformly in T, essentially for an epsilon, and but this behaves like so. This more or less morally belongs to like. It is not true, okay, but morally, essentially, is almost there. Okay, then its square it will converge to some limit in C minus 1 minus epsilon, and y will converge to its limit in C minus 1. Okay, so now you have really worse irregularity, and that's tricky, and actually that's a problem because I already told you that for Z I cannot get better than H1. Okay, so even this guy is problematic. This guy is not good. I cannot control it because for this I have only 1 degree of regularity. Maybe the power is okay, but I mean it's not even okay the power, but okay, the regularity is good. And so these terms I cannot control, so I want to cancel them. Okay, that's the point now of new ingredient you want to. Okay, so we want to cancel. We have to cancel at least these 2 terms. Okay, the 2 and because I cannot control them, okay, with the good terms, so I want them away. And let me explain to you how does it work for this one, because it's easier. Okay. It's a bit easier. So how I can cancel this term? Now the idea is that I need somehow to put it in the. So what I want to do is that I want to do a shift of u, so that this quadratic term produce a cross term which cancels that. So okay, you just I want to complete a square. Look at as you want. Okay, so just you have this is quadratic in z, this is linear in z. I want to complete the square. And here I will do a transformation which will make it linear, and then I want to play the same game. Okay? So maybe this can be made systematic, and you can subtract all the by all the data. Maybe one needs regularity structure then to be systematic. Okay, so but this now I have to compare with this, and this is you see this is something which looks like US, and this is the spatial, as you know. So looks like something, so it's not in the same language, okay? This is an integral over time, there is no integral over time here, so I cannot just match things up and cancel. So what I need to do is that I need to develop this term along the scales, okay? This is computed at scale t, and I want to write it as an integral. And then I use Ito formula, okay? And Ito formula, so this is spatial integral, okay? Also. In the time integral, I always put the
Epsilon squared, no? Up there.
yeah.
No, there.
Ito formula, so you use Ito formula, and the point, so simplification is given by the fact that this is a martingale. Okay, so weak products are martingale because they are Hermite like Hermite. Okay, so this is a martingale in T, and now you compute Ito formula. I neglect the boundary term, so let's see what happens. And this is differentiable, okay? It has derivative in F2. And so it looks like something like this. So this is the integral between 0 and t. And then when you differentiate this, I will ignore the martingale part, because anyway it goes to 0 when I take the expectation. Okay, so the martingale part you can ignore. So when you differentiate this, that's fine. You don't get. Let me think what I'm saying. Yeah. And then you have now you have this at scale t, and you have the derivative of z at scale t. This is the partial integral. Okay. I'm thinking, yeah, and then you have the martingale. Okay, so and this term can be eaten with this, because what is this? What is this? This is 1 minus Laplace to the minus 1/2 sigma of t of d u of t. Okay. So now the idea would be I complete this square. Okay. And this operator is self-adjoint. Okay, so I can put on the other side. Let me give it a name. So this operator altogether I call it gt. So this is gt ut. And then I can take these two terms. So ut and then u. And I can put them together. I can put them together to give. So this gives integral gives t. Okay, 0 infinity, and then I have something like the integral cube 0 gt, t less than big T, or qt, ut, plus 1 half ut squared. And then you have integration. So now I do the change of variable. So I call it, ut, I call it minus what is there, t bigger than t, jt, I cube, t. There is something wrong. Let me think. No, I think it's fine. No, there is something wrong. No, it's not minus 1. It's minus. I'm lost. Sorry. No. Yeah, no, it's okay. Everything is fine. Yeah. And I have this and this. Sorry, I was distracted. Okay, so I just do this change of variable. Okay, so now when I expand the square here, this got squared, but essentially I don't care because it does not depend on anything. And then you have the cross product, and I think it will cancel that one. And then you have this square. So this computation is too difficult for me. I cannot do it like it's like this. Now you complete the square, but there is to adjust. Maybe there is 1/2 to add somewhere because to work. But at the end of the day, the moral is that this object will become something which is independent. Something which looks like jt by qt to the square, integrated in time, plus something which is b to the square.
So here we pretended lambda as 1, right?
Yeah, sorry, I lost track of lambda, but there were a lambda here, okay? So if there is a lambda here, there is a lambda here, and then there will be lambda there. We see that, but this was painful because at the beginning I wrote, every paper I write is without lambda. Then I have to go back because people are asking, where is lambda? And then I go back and I have to put all the lambdas. But okay, it's there, and then here it's independent of lambda, and here you will have lambda square. Who asked the question? Okay. Yeah, I mean, the point, so sorry, maybe this is, I mean, it's just you have to complete the square. The idea is that if you translate with this quantity, maybe a factor or change the sign, I don't remember, you get rid of the cross term. And you get a term which is independent of u, and this is essentially harmful, because when you take expectation, give you a number. If it's infinity, you remove it by subtracting a quantity, you don't care, and it gives you another control. Okay, so now the idea, the other term can be removed in the same way, okay, but will require some more tools to do it, okay, because it's quadratic in Z, so I cannot just do it as simple. So I will discuss it maybe a moment later. But let's look what I'm doing now, okay, so the idea will be that these cross terms, I cannot control. So it means that they can be very large or very negative. Okay, that's the problem without any a priori information. And I want to use the a priori information. So the only a priori information I have is that I have the good guys and I'm doing the minimization problem. Okay, so this is this idea we also use with Nicholas in the paper of KPZ. That is, you can renormalize stochastic control problems. Okay, and the idea would be that if in the stochastic control problem there is a term which you don't like, which is which is trying to be very large, this telling you that your control is start to be singular, okay? Because the control, so essentially what's going to happen is that this u is start to go outward from L2 to beat that guy, okay? So the control problem has to be changed because it's not set up in the right space. Okay, the right space is that you don't have to look at the control u, you have to look at control V, control U, which have a very specific structure. That is, they start with something plus, and then you are free still to control. Okay, but the initial part of the control, or the most irregular part of the control, has to be very precise, otherwise you screw up the normalizations. And then more regular part there. And when you do this, you have a new control problem now. Okay, now essentially you are controlling V, not U. And but then this U will appear, this guy will appear everywhere, because essentially Z is a function of U. Okay, so Z will have a structure. So this is what I was saying before. Okay, I want to use that. So that's what. Maybe this can be done systematically. Actually, it's a good, would be a good idea to do it. But even phi4, the dynamic phi4, nobody really tried to write down systematic expansion more than what is needed to get things done. You see what I mean? No, I mean, because they want to track lambda, no? So you would like to have a systematic expansion in lambda with the solution. But maybe it's possible. Nobody yet did. So now you see this is the new one. That's, okay, so now you have done a change of variable, means that now the t now z is a function of u. Okay, so you have to just z. Remember, it's just the integral. In my notation is just this integral here. Now js is 1 minus Laplacian minus 1 half sigma s. So you are filtering some frequencies and then you are coloring a bit. And then, so this will give you something. Now if you apply there would be like, now there are two, yeah. This is t smaller. You have t smaller than t minus lambda, and then you have gt square, and then you have y cubed t dt. And then you have a plus, and you have a new control, you have js ds. Okay, so there will be a term like this, which looks like the tree, so you give it a name. This guy, you call it y, t. You have to make this. And this is like the tree. If you want to give it a name, it looks like this, okay? Because it's really the product of three free fields, and then you propagate still more, okay? And this is exactly as the same scaling as the parabolic propagate. So it has the same regularity. Okay, this guy will belong to 1/2. Okay, so you see, this guy is not in H1. Okay. It's better in integrability, but regularity is blocked at this level. Yeah, so this is the signal that the control problem is singular with respect to the previous one, and I think this is also the signal that the measure is singular, okay, because it tells you that the interacting field is the free field plus this term plus something else, but already this is not in the Cameron-Martin space. It's random, so it's not so obvious to me that it can be proven, but it's reasonable that you are moving in direction which are not in the Cameron-Martin space, and then the measure is singular with respect to the Gaussian. And I think, yeah, to handle the other one, you need to have more work. Okay, so this cancels the first one. Then you have to believe that all the terms that remains, they can be controlled. Okay, and it can. So, but now the good terms are different. So the tricky stuff is that the good terms now are ZT L4. So the good terms look like this. So this V is this new V, okay, which enters into Z in this way. But the L4 norm is on ZT. Okay, and I think I tried to expand, and at some point I realized that was not a good idea, but okay, could be maybe a good idea. It gets things more complicated, okay? So the game to play is that every time you have to control something, you have to be sure that the only powers Now the game is more complicated, okay, because you start to have objects which are integrated in time, not just evaluated at the last time, okay, so you cannot, and there is no way, which I know, okay, so the problem is that ZT, for example, cannot be controlled. I think it's even, I don't know, okay. That's part of the problem also in gamma convergence. Okay, I cannot control these things. So along the flow, I cannot control with the final value. Okay, but I have only the good term, the final value. So as soon as I have a z which is not computed at big T, I'm lost. Okay, so the game is not to have this term around for which you need the higher integrals. Otherwise, you are lost. And that makes things a bit trickier later on. Okay, but that's a difficulty which I don't know how to solve.
But that,
Okay?
I mean, can that be true? That can never be true, right? Because you can just do this.
It's for me. I mean, even with a constant, I don't care. But even with something else, but I mean, some way to control this with that. There is something which is true because you have this. Yeah, that's a tricky problem. I don't know.
But you need some control in time on the left-hand side, right? I mean, you can't just.
You see, the point is that, so what you're doing, you are summing pieces which are more or less correlated in Fourier space, okay?
Yeah.
But you want to control L4 norm. So this is problem like in harmonic analysis, okay? And there are estimates, like there are this maximal function estimate, which tells you essentially that, yeah, I think we can stop. I mean, maximal function estimate tells you that you can take some kind of quadratic variation in Fourier space, essentially, and this control the LP norms. And in that sense, that's easy. This parameter is just getting bigger, so the quadratic variation is just getting bigger. So there should be, these are two-sided estimates, okay, essentially the maximal estimate for little Pali square functions. So you have an estimate from above and from below. So, and here the parameter is moving, okay, and if they were really like little Pali blocks would be okay, but I think if they're very separated, I can handle, but if they're nearby, I don't know. It's a complicated, I don't have any easy solution, if you have some solution.
But when you z is just the u integrated in time, no?
Yeah.
And how can that be? I mean, couldn't the u just do something like that and then cancel, and the final thing could be 0 and the final thing before cannot be?
No, because they're on different scales, so a priori they are orthogonal. You have this
That's
12
because you
function.
introduced the sigma, yeah, okay.
Yeah, there is the sigma in front.
Okay.
No, but the problem, intuitively for me, the problem is easy. Every scale you are doing just different things and they don't interact, but analytically I cannot prove it. So because you have small interaction, blocks which are separated, that's fine, but blocks which are nearby, they interact and I cannot estimate it. Anyway, I think we stop here. Thank you for listening.